Good morning. It looks like we have at least 4 now already. That seems to be working. I'm just going to wait a few minutes till 10 o'clock and get everybody online. That's 6 online. Let's see. Now, for those of you who are there, we'll have the chat going on in Google Hangout here. I believe, yes. Great. Well, it looks like we've got about half the class online here, and I'm going to go ahead and start. Excuse me. Again, I apologize for the short notice on this, but I think this will work pretty well. I wanted to make sure that we get through this section on modifiability. It's an important one, especially for large systems moving forward. You know, that will have a long lifespan. Oops. Hopefully that's coming through there. I'm just going to switch over to the to the other screen. Hold on one moment. And I just have to get our screen back. There we go. The whole point of modifiability as a quality is the ability to anticipate and handle change. And we have several questions to ask ourselves, which is this a system that is likely to change? And if it is, how often will it change? And how much will it cost to make those changes? And these questions are all within the context of the type of system that we're looking at. And as we start to think about the functional behavior that we have in this system, we may say, you know, functionally, it's not going to really change very much. But we may improve other types of qualities. For example, algorithm for calculating something that's faster, but still generates the same result. And we might say, well, it'll change a few times in the beginning, but after that, it's likely to stay the same. So we don't want to spend too much money dealing with it. And in the end, we have to determine how much it's going to cost to make the changes. If they're relatively infrequent, the cost of actually going in, changing some code, building it again, testing it, deploying it again, may not be so great. If it tends to change very quickly, and small bits of it tend to change quickly, for example, operating systems or your iPhone software or your Android software, you might invest in mechanisms that allow you to change the software relatively quickly and relatively low cost once you've made up for the cost of building in this ability to manage the change. And on the slides, which are also online, by the way, the slides are also on Blackboard there, the same slides we're looking at. The only difference is on this slide, there's a ball instead of the standard picture. And I'll post that one slide change there. Now, you may have seen this before, and I've talked a little bit about these spheres as a rough model for the complexity of software. And it's a good one to have because it captures the notion that software is not two-dimensional and that a lot of the complexity arises from the multiple connections that exist between the components in the software. As a result, you can see that hold on one moment, there we go, that the surface is roughly equivalent to the function points in the system. And the surface area is about the square of the radius. Now, if we consider the radius to be the capability of the system or the functions of the system, the functional requirements, we see that the function points required to support it often increase approximately with the square of that radius. Why is that? Remember when we talked about the requirements, we said, well, for a given functional requirement, in order to achieve certain qualities, non-functional requirements, we may introduce yet other capabilities in the system to support those. Therefore, you don't necessarily have a linear relationship between the functional behavior of the system and the complexity of that system. Now, worse yet, if we think about the volume as the actual amount of software written, it tends to increase with the cube of that capability, which means as a single unit of software gets larger, it gets increasingly more complex. And one of the things that they don't talk about much in the book is that it is the complexity that makes the system difficult to deal with. And the more function points we have, in other words, the more capability the system has, the more complex it gets. Now, we have these questions which are captured in this general scenario, using this model that we're going to be using for all of the qualities, which is that in general, we have as a source of some change request, either the end user or the developer or maybe a system administrator, anybody who has the ability to influence the system. And they may request changes in the functionality, in other words, functional behavior. One of the qualities, I want the system to do what it's doing, but just go faster. Or I'd like the system to do the same thing, but just not fail as often. You iPhone 10.0.2 users know what I'm talking about. Or maybe, you know, we want to keep the system the same, but we're going to swap out a particular graphics card for another one to make it a little bit faster, but it doesn't change anything. And what we're changing is code. It can be data. In other words, the initial set of data. It might be configuration files. It might be hardware. Those are the artifacts we're actually changing. And what we're going to spend a lot of time talking about is what happens in the environment. In other words, is it at design time we're making the change? Is it at compile time we make the change? At build time? At runtime? Maybe even at during runtime, from event to event, we may be modifying the system. Now, I'm assuming that just a quick process check. If you cannot hear me, or if you can hear me, somebody send me a quick text or email, just so I can make sure that the voice quality is okay. I believe it to be, because it shows that it's registering my voice. Now, in response to a particular request to change, we may rebuild the system, test it, and then deploy it. We may change a parameter in a configuration file and restart the system. We don't necessarily retest it. Maybe we simply change a binding in a DNS server, which is similar to a change in a configuration file. And the next time they hit a URL, it will resolve to a new DNS. Now, in the end, we're going to be able to measure that and understand how expensive it was to make that change. In other words, how long did it take, and therefore the cost, because there's always a cost associated with labor. But it might also be the extent of the change. If I make this one change in this module, how many other modules were affected as well? It might be that the cost was to go in and make changes to code, recompile it, redeploy it. That might be very expensive. If it just takes me 2 minutes to go in and change a DNS entry, and just the next time it's hit, that's relatively inexpensive. Okay. Now, we're going to also talk about the initial costs of being able to support modifiability as well. Now, in order to make a system modifiable, we need to deal actually with a number of different issues at the same time. And typically, when you're looking at a new system construction, you are going to be anticipating approximately the rate of change in different parts of that system. If I'm looking at a medical imaging system, some parts will tend to change more often than others. Some parts not very much at all. In fact, there are going to be some parts that you don't want changing, because you might have to have them recertified by the government, as I believe we mentioned in the first or second lecture. And so as we start to look at, for example, our air traffic control system, we're going to be thinking about how often do I have to change this system? How much do I want to spend making it modifiable? And where is it likely to change? Well, the first way we tend to think about helping a system be modifiable is simply carving it into smaller pieces. From your very first simple programming assignments, you were encouraged to divide the problem into smaller pieces, solve those problems, and then build it back up again. And so the notion of taking a single monolithic system and breaking it into pieces is an obvious first step. However, as soon as you start taking the system into smaller pieces, you are going to increase the complexity because you have all these pieces to deal with. Each piece has to be managed in some way. You have to keep track of it. If I change a single piece, I have to determine what dependencies exist between that piece and other pieces of the system. And I can't arbitrarily divide it up. I need to think about where what are called shearing points are in the system. The notion of shearing points sort of comes from mechanical engineering or even geology, and that is, where are you likely to see shifts? If you think about the two plates in plate tectonics in geology, and they move along each other along a fault, we get earthquakes, for example. In bridges, we create shearing points and expansion joints so that if one part of a bridge shifts, it doesn't try and rip it out of the foundation. So in any well-engineered system, we look for those divisions in the system where rates of change tend to be different, and we attempt to accommodate that. And so, for example, in a graphics system, the functionality may not change that much, but the underlying algorithms may change. I may have improved algorithms for calculating area or whether a dot is inside or outside a boundary. And I may have better software, better hardware for actually doing the rendering, and that may change fairly frequently, but the functions don't. So I'd like to divide those into separate layers. As a result, our first approach is to start to think about what are interesting divisions of responsibilities. And in fact, generally, this is a design tactic that we use, or design decision we have to make, which is, where do those responsibilities lie? And how do they interact with each other? Which brings us to the notion of cohesion. Now, cohesion and coupling, which we're going to look at in just a moment, are two of the great forces when we're designing a system. They're roughly equivalent to proportion and, scale and symmetry in building architecture. And you'll see why here in a moment, I believe. Again, with my blue sphere representing the notion of our software component, I could potentially build a system as one giant mass of code. It doesn't have to be broken into smaller pieces. We immediately start breaking systems into smaller pieces when we attempt to address different architectural qualities. In theory, that one big blob of software could accommodate all of our functions if it had typically infinite resources in terms of speed and responses and availability, etc. So when we think about cohesion, we're thinking about the semantic coherence of a particular module. We're saying, do the functions that exist within this and the data that's supported, are they conceptually related to each other? Because what we find is, if I have a sphere, or if I have a group of software that has two independent concepts in it, it's quite likely that if I change one, then I wind up there's no relationship to the other. So that whole module has changed, even though there are two groups of functions that really don't have anything to do with each other. And so what we try and do is we try and divide the sphere into something that's a little more cohesive. And we might break it into 2 or more subcomponents that are more related to each other. The items within them are related to each other, such that if a particular function changes or a particular quality changes, I may only have to address one of those components. So we're trying to localize those responsibilities. And when you think about it, that's really what we're doing when we think about objects. And one of the reasons that the object model was so popular, or I should say, one of the reasons that object model, the object-oriented paradigm is so popular, is that it helps us address the issues of both cohesion and coupling simultaneously. For example, when we think about what an object is, it is data and related data that help us create a model of some entity in our domain, and a set of behaviors that define the set of possible state transformations of that data, and typically capture the behavior or the responsibilities within that system. And those behaviors and that data are closely related, because it's specifically those behaviors that are needed to change the state of that data, and that data is related conversely to those behaviors, because it can only be changed by those behaviors. And so objects, both in the very small and in the very large, are a good way of capturing the notion of cohesion. A poorly designed class is one in which you have 2 sets of unrelated data and potentially 2 sets of unrelated behavior. And we often see that when we see, for example, an object that has the data responsible for, say, measuring temperature, and then the data and behavior responsible for displaying it. If you try and jam those into the same class, you're going to find, well, it's not very cohesive. One thing sort of has to do with representation. The other thing has to do with capturing the essence or the semantics of temperature. And while they're associated, they are not cohesively one concept. So the notion of cohesion, while it has sort of a slippery definition, is one of the most important aspects of decoupling and breaking a system into smaller parts. But working directly against it is the notion of coupling. And we very often use the phrase cohesion and coupling at the same time, because they are 2 forces that work against each other. There's a dynamic tension, as we say, between cohesion and coupling. If I attempt to create a very cohesive elements with high cohesion, I tend to break them down into small pieces so that only the data and behaviors that are related to each other are within a particular module. But as I break it down into smaller pieces, by definition, I am pushing out behaviors or dependencies that exist in the system into other modules. And that means I now have this dependency on these other modules, and I'm coupled to them. In other words, if I make a change to, for example, one of those modules, then very often I wind up having to make a change to the other, especially when it comes to behavior. And that's because I'm coupled. I rely on this other component to support some of my behavior, and I have to make sure that that behavior is still appropriate if I make a change to myself. So the problem is that as I increase my cohesion and create slightly smaller units, it's quite likely that I'll also drive up the coupling in the system, and then I have to deal with that. And we can do this with using the notion of layers, where I can control coupling in the system. And we're going to look at that when we look at patterns. But we're also thinking about how we can reduce coupling by deferring those relationships. In other words, by hiding those relationships. And we're going to look at publish, subscribe in just a moment as a way of doing that. So coupling is the degree to which I'm dependent on another component or module. And you can see that cohesion and coupling, if my cohesion goes up, often my coupling goes up. But we don't like a lot of coupling because when I go to make changes to this system, I typically have to change other components. On the other hand, cohesion, when it goes up, it makes it easier to change a component because typically the change is only related to that component. So we try and strike a balance in cohesion and in coupling. And I've also noted that coupling is the name of a very funny, what I consider to be very funny, British comedy. There's an American version that's not funny at all, but the original British version is extremely funny. Now, one way that we can decrease dependencies is to push the binding out, and we're going to spend a lot of time talking about binding here. We can do this by hiding the dependency through an intermediary. And one of the most common models we see is seen in the publish-subscribe pattern. We can also call it the observer pattern, is another name for it. It's used extensively in the model view controller triad. In fact, it's used in so many places that for example, the Java libraries, the basic Java object class has built into it the notion of publish-subscribe mechanism. And we see it in different forms depending on the complexity of the system. What we do is, if a particular subject is being observed by a number of subscribers, I can decrease the coupling between the subject and the subscribers or the observers of that subject by delegating the responsibility to the subscriber list and saying, well, if the subject changes state, I'll notify the subscriber list manager, and it in turn goes out and updates all of the subscribers and says, hey, you know, that subject just changed. Why don't you run back and get the appropriate data from it? And it turns out that it's a very flexible way of connecting two objects because the subscriber list has all of the intelligence built into it having to do with who are subscribers, when do they get updates, how often do they get the updates, I should say. And it allows the subject and the subscriber to be decoupled, and it's mediated by the subscriber list manager. Now, this brings up exactly the issue that we are going to see over and over in modifiability, which is, wow, this makes it really easy to add new subscribers. They simply subscribe to the subscriber list, and they will get an update from the subject, and the subject never has to know about it. Well, that's handy. But I've had to build in this capability. I've had to build a subscriber list. I've had to use memory in order to store all the different subscribers. The subscribers have to know to go and add themselves to the subscriber list. They have to know that when they get an update event that they go back to the subject or through an intermediary to get the update in the subject. But it's very flexible. So here we see an example where there was a fairly significant cost in order to do subscription management, mostly in terms of the initial setup. There's some overhead to actually subscribing to the list. There is some overhead in unsubscribing from the list. And even more importantly, there is a design cost that says, wow, I have to understand how the subscriber list mechanism works, the publish-subscribe mechanism works, and I have to adhere to the protocol in order to make that happen. So I have to understand it, and I have to implement it. So there's a reasonable cost, but it gives me a lot of flexibility. Even at runtime, I can dynamically subscribe or unsubscribe from changes in the subject. So it gives me a lot of flexibility. So this notion of deferring binding turns out to be extremely powerful. And we started to see it in the interoperability discussion. As I said earlier, one of the things that we see is that the notion of availability and interoperability and modifiability, and we're going to see many of these qualities, are interrelated. We get some of our modifiability by being able to defer bindings as late as possible. But the later we defer a binding decision, typically it's more expensive. So our modifiability comes at a cost. So when can we change systems? Well, I can change a design before I've even built the system. It's relatively inexpensive to do that. I can make changes to source code and recompile it. So at compile time, I can bind my design decision. I can make my modification at compile time. And when I recompile it, the change will be reflected in the source code. Not too expensive, but every time I make a change, I have to rebuild the system and redeploy it and retest it. So there's some cost in that. Now I can parameterize some of the compile. For example, I can compile in test code and then take it back out for deployment. Or I can parameterize it at build time. I can swap in a different library. For example, you may have a different library built in at runtime that's optimized for production, but you use a different set of emulators while you're actually developing the system, so I can parameterize it at build. Very often systems are configured at startup time. They read a configuration file once at startup time to determine the overall configuration of the system. For example, certain boundaries or certain parameters, maybe which components are going to be active at that time, but then they don't tend to change for the remainder of that runtime. Or I can push it out even further, as we were talking about with DNS entries. I can push it way out to runtime where I can change the configuration of the system at runtime and have the system adapt at that time. For example, using DNS, domain name serving, I can change the endpoint of a URL, and the next time I hit that URL, I will be at a different target. I'll be going to a different endpoint. That's very flexible. I can swap out components at runtime, and the rest of the system doesn't have to start. But as we saw with DNS, there's cost to that. One, I have to have the DNS server. Second of all, I have to go get it, and it has a cost of, one, just the execution of it. There's also the hidden time, or what the latency of actually sending the message to the DNS server and returning it. There's a lot of error checking that has to go on. There's error handling code that has to be written to support what happens when something doesn't work. It's a lot easier to find an error at compile time and know that it's always going to work, rather than all the code that surrounds runtime error checking. So there's an example of where the cost starts to go up as we get that binding time further and further out. We also see deferred binding and polymorphism. So, for example, I can add in new types of classes of objects, and as long as they conform to the interface standard for a particular general class of objects that all share the same interface, the runtime language environment will bind the appropriate message to the appropriate methods, as we saw in class the other day, at runtime. So polymorphism is a way of increasing or improving the modifiability of the system. I can add new classes of objects with new implementations, and as long as they have the same interface, they'll plug into a particular environment. Another example is actually one of the senior design projects that I have in my senior design samples, and it can have a number of different types of assessments that can be added in at runtime, actually, even. And so I could have an assessment module that determines the number of uhs and ohs and ms that are in a voice sample. I can have another assessment sample that measures the number of long pauses, another assessment module that measures duplicate words, for example, another one that might measure cadence or tonal qualities of the voice sample, and then the total sample is a summation or some function of all of those individual assessments. But it allows me to modify the system relatively easily without changing other parts of the environment and necessarily even rebuilding it. I can add them in at runtime, as long as the assessor tool itself says, let's go out and see what assessment modules I have plugged into this at this time. And that starts to look a lot like this notion of what is actually called a toaster model, for exactly the reason that you might think about it. Those look like little pieces of toast being inserted into a toaster. And what it does is it allows me to have a basic framework of a system and then modify it by plugging in new capability in that environment. And architecturally, this is going to be some of the most important decisions you make, because what happens in architecture, not surprisingly, is that early architectural decisions are, one, far-reaching, and two, get progressively more expensive to undo later on. That means, for example, that if I decide that I am going to have a very late binding environment where I can easily plug in different modules, there will be some initial cost to it, but later on, I'll continue to have lower cost of adding items in. If I break my operating system into lots of smaller components that can be easily inserted into the runtime environment, it will be easier to update the operating system because I only have to load those single modules in order to keep the system running. I don't have a lot of bandwidth required to download and install new versions, just small ones. You see that in particular on your phone system, on your handheld phones, where they want to reduce the number of components and reduce the size of the components to make it easier to make it easier to modify the system. So we have this cost trade-off that we have to deal with. We love late binding because it's like anything else. If you can push off a decision, that's always the better thing to do. But late binding is typically more expensive to implement. I have to implement the infrastructure for it. I have to test that infrastructure, and I have to deal with runtime errors. And dealing with runtime errors can be pretty expensive, because what if I'm out there and I have in my system, I have a particular component that, say, supports a type of computation, and it's not there all of a sudden. Now what do? I'm suddenly out there in the middle of doing some sort of task, and I'm missing a piece. How do I recover from that? Can I recover from that? And if I can, do I go back and try it again? If I can, do I keep track of the number of failures? We gave the example with the DNS late binding and the interoperability. We said, well, you know what? I failed to get a response back from the DNS, so I'll just keep using my current value. But I'm going to try it again in a couple of moments here. And if I still don't get one, I'm going to try it one more time. And if it fails 3 times, then I'm going to say, look, we've got a bigger failure here. We got to restart the DNS server and give this another try. So all of that code starts to get pretty expensive. So early binding decisions are less expensive because I can make a lot of decisions early on, but it's more expensive to change it later on. As a result, If things don't tend to change, or it's unlikely to change, then I'd like to bind those design decisions early on. If it's going to look like it's going to be pretty dynamic, I'm going to push that binding time out. So certain things in our air traffic control may have to be fairly modifiable. For example, the ability to handle flight planning, or the ability to change the way certain types of communication is done. The overall architecture of the system probably won't change, but we expect the system to last a very long time. It's expensive to develop and change those. So we say, you know, we're willing to add in a fair amount of capability for managing that change. Now, it may not be late dynamic binding all the time, but we say, you know what, we're going to make it pretty modular. We're going to have a lot of different modules that we can change out fairly easily. So well-defined interfaces, but nicely encapsulated design decisions inside those. Now you should be, we should be back and going here. Whew. Let me just back up on him. Bad communications going on there. So in our system, we'll be thinking about layering. We'll be thinking about good modularity. We'll be thinking about how easy is it to change certain components without affecting others. So good cohesion and coupling. Another example is the notion of the enterprise service bus. And the service bus is an example of an architecture which creates a very modular environment that's very dynamically bound. And in service-oriented architectures, or SOA architectures, we define a number of service providers, and in the picture it's labeled as 1, 2, and 3 here. And the consumers discover these services through a directory service, which we'll talk about later. And the directory service links the consumer with the provider of a service. And so the endpoint is basically being bound at runtime and allows the consumer to take advantage of one or more services by connecting to this common bus. And when we talk about a service bus, we're saying that there's a basic communication mechanism that allows the consumer to talk to the provider. That may be over a TCP/IP network. It may be over HTTP. It may be an XML message that being passed along any number of different lower level communication paths. But the net result is that I have the ability for the consumer to talk and request services from the provider, and the provider to return data or acknowledgments back to the consumer over this bus. And the advantage of this architecture is that, one, it can be very wide-ranging. In other words, if that bus is a wide area network, such as the internet, The providers can be provisioned in any number of different locations, as can the consumers be located almost anywhere. And as long as the service is discoverable, the consumer can take advantage of that provider of that service. Now, the essence, one of the important parts of this, though, one of the essential parts of this is the ability to discover those services. And we see in any time we defer binding, we have this requirement that we're able to have a directory service of some sort, and that directory service supports the notion of being able to have a consumer say, I need a particular service, such as color printing, or making a car reservation or a hotel reservation, or adjudicating a healthcare claim. And you are going to return to the consumer a pointer to that service provider, and very likely a set of services that a detailed list of services that that provider supports and how to interact with it. And that discovery service is an essential part of this late binding mechanism. Now, we see this in a very small example with the domain name server, the DNS server. It supports one service, which is to resolve the name to an IP address. And we typically discover it, and we bind that service at network startup time. You go to your network stack and say, hey, where's my DNS provider? And then I go out and get the name. But I can create, say, a complex system for doing travel management by having a number of providers that do car reservations, hotel reservations, ship reservations, train reservations, and payment systems, for example. And the consumers could be any number of different types of travel services, all connected to a common bus. So very dynamic, very robust, but relatively expensive. All that communication costs something. Provisioning the service bus costs something. The protocol for identifying a service, attaching to the service, sending the message all costs something, but it's very, very flexible. So we see that in modifiability, the key concepts to understand here are, as the system gets bigger, in order to keep it modifiable, I will have different tactics for addressing this. One is breaking it into smaller pieces, smaller sizes, individual modules that then also generate other components. Remember, a module might be, say, a .java file. The component I generate might be a graphics component, for example, that I run that supports all the graphics calls. And I can break them into smaller pieces. But as soon as I start breaking things into smaller pieces, I have to somehow manage those pieces and keep track of all the dependencies between them. In large systems, let's say I have 80,000 modules in a system, I might have a large number of dependencies between them. So I have to apply the notions of cohesion and coupling. Cohesion meaning keeping the related parts together, and then decreasing the coupling so that if I change one module, I don't necessarily have to change another module. And one of the strategies I can use to keep those dependencies down is, one, thinking about layering, which we'll talk about on Wednesday, and B, thinking about the notion of deferring the binding decision or creating an intermediary between them so I don't have to make that decision or make that commitment early on. And then finally, this notion of late binding, which is really the Cadillac way of making your system very modifiable, but with an increased cost, as we saw, say, for example, back here, where as you push out the time, the binding time, the cost tends to go up. There are some examples where it's not necessarily true, but generally that curve is fairly accurate. So if we go back to our general scenario, we're going to be thinking about the modifiability of our system, and we tend to think about it fairly early on as one of the key qualities that we're thinking about. If we're doing a research-oriented system, for example, where I'm going to be making a lot of changes, I'm willing to take both the design cost and the usability costs that go along with a highly modifiable system in order to be able to quickly experiment with different capabilities. We had a kind of a funny quote from a researcher at General Electric once, and we were talking about how flexible the system should be in terms of being able to add new capabilities to an MRI system. And he turned to us and he said, in the end, the system should be infinitely flexible. And we actually had that made into a metal plaque and hung outside his door. In the end, the system should be infinitely flexible. And of course, that would be the ultimate, but there's a huge cost that goes along with that. So we're going to be making that decision about what kinds of changes we expect to happen, where the shearing points, when we'd expect to make those changes. Are they at design time, compile time, build, run time? Trying to push out that, we're deferring that binding time as late as possible. And thinking about what tends to change in the system. It may be just hardware. And how we tend to make those changes. And then finally, what are we willing to pay for that? What's our measure of success? Is it the extent of change that occurs? Do we want to minimize the extent of that change? How long should it take? There are requirements to say you got to be able to make an update to a security change in less than 24 hours. Are there changes to other qualities? In other words, if I make a particular change, will it change the responsiveness of the system or the availability of the system or other types of qualities? So I know you have another class now, and we'll be covering a little bit more on some of these patterns on Wednesday. And again, I apologize for the short notice. We will see you on Wednesday.